Hello students, welcome to today's physics session. In this lesson, we'll dive into the topic velocity of sound and its variation with medium, which is a part of your Class 11 physics curriculum. Let's break down this concept step by step to make it simple and engaging. Section 1, Introduction to Sound Waves. First, what exactly is sound? Sound is a mechanical longitudinal wave. This means it needs a medium to travel, like air, water, or solid objects. It cannot travel through a vacuum. The general formula for the velocity of sound is v equals square root of b upon rho. Here, v is the velocity of sound, b is the bulk modulus, which represents the medium's resistance to compression, and rho is the density of the medium. In simple terms, the stiffer the material and the lower its density, the faster sound can travel through it. Section 2, Formula for velocity of sound. The formula again is v equals square root of b divided by rho. This is a general expression derived using gas laws and assuming adiabatic compression, which means there's no heat exchange with the surroundings during compression. Bulk modulus, as you now know, measures how much pressure is required to compress the medium. The higher the bulk modulus, the faster sound travels. Density, on the other hand, slows sound down, so the ideal medium for faster sound is one that's stiff but not too dense. Section 3, Velocity in gases, Newton-Laplace formula. For gases, the formula gets a little tweak. It becomes v equals square root of gamma p upon rho. Here, minus gamma is the adiabatic index, which is the ratio of specific heats Cp upon Cv, p is the pressure of the gas, and again, rho is the density. This is called the Newton-Laplace formula. Now here's something interesting. In gases, the speed of sound is actually independent of pressure, because when you apply the ideal gas law P upon rho equals RT, pressure and density change proportionally. Also, for every 1 degree Celsius rise in temperature, the speed of sound increases by approximately 0.6 meters per second in air. Section 4, Variation with temperature. Now let's talk about temperature. If you increase the temperature, molecules move faster. This leads to an increase in the speed of sound. Mathematically, it's represented as v is proportional to square root of t. That means velocity is proportional to the square root of the temperature in Kelvin. So if you double the temperature in Kelvin, the speed of sound doesn't double, but increases by about 1.41 times. Let's take an example. At 0 degrees Celsius, the speed of sound in air is around 331 meters per second. For every 1 degree Celsius rise, this increases by around 0.6 meters per second. So at 20 degrees Celsius, the speed becomes roughly 331 plus 0.6 times 20 equals 343 meters per second. This is why sound travels faster on a warm day. Section 5, Variation with density. Now what happens when density changes? Let's say you compress the air or change the medium to something denser, like water or steel. If the density increases and bulk modulus remains the same, then sound travels slower. But usually when density increases, bulk modulus also increases, sometimes even more rapidly. This means the speed of sound might still increase depending on how bulk modulus changes in relation to density. The formula again to understand this is v equals square root of b upon rho. So if part of b increases faster than rho, velocity increases. Imagine pressing down a spring. If it gets much harder to compress, it means bulk modulus is going up, and sound can travel through it faster. Section 6, Speed in different media. Now let's compare how fast sound travels in different media. Here are some approximate values. In air at 0 degrees Celsius, 331 meters per second. In water, 1,500 meters per second. In steel, 5,000 meters per second. What do you observe? Yes, sound travels fastest in solids, then in liquids, and slowest in gases. Why? Because solids have a much higher bulk modulus, meaning they resist compression much more. That allows sound to travel rapidly through them. This is why when you put your ear to a railway track, you can hear a train coming from far away, much earlier than through air. Section 7, Summary. Let's summarize everything we've learned. Sound is a mechanical wave that requires a medium to travel. Its speed depends on two main properties, bulk modulus and density. In gases, speed is proportional to the square root of temperature and is independent of pressure. Sound travels faster in solids than in liquids or gases. As temperature increases, so does the speed of sound. An increase in density usually slows down the speed, unless the bulk modulus increases more significantly. That's it for today's session on velocity of sound and its variation with medium. I hope you understood the key concepts and formulas. Don't forget to revise the formulas and practice with real-life examples, like comparing how sound travels through walls versus air. Don't forget to subscribe to the channel. Until next time, keep exploring physics and stay curious.